Hi, and welcome to our group's capstone presentation on the development and optimization of a polylactic acid polymerization reactor. Plastics play a critical role in modern society with applications in packaging, textiles, electronics, and construction, just to name a few. In North America, plastics production accounts for over 12% of total materials produced, with an annual production of 460 million metric tons, which in turn contribute to 20 million metric tons of non-biodegradable plastic waste each year. Growing environmental concerns regarding plastic pollution and its impact on climate change have made sustainable alternatives increasingly necessary. And one such alternative is polylactic acid, or PLA, a biodegradable polymer derived from renewable plant sources, which is already being used in various industries, including the medical, textile, and manufacturing industries. In our project, we'll be focusing on designing and optimizing a reactor model for the large-scale production of PLA.
You might be wondering, what is a polymer? A polymer is a long chain of individual units called monomers, linked together by a chemical reaction called a polymerization reaction. This reaction is started by a chemical called an initiator. Each initiator molecule starts an individual chain. The polymer chains will keep growing until there are no monomers left to be added. Polymer properties are mostly determined by the average length of the polymer chains formed. This is measured by the average molecular weight, which is just the average chain length times the mass of an individual monomer. The goal of our project is not just to design a polymer reactor, but to make a general model that can be used to design reactors optimized to produce any desired molecular weight of polymer. The complexity of simulating polymerization reactors arises from the reactive flow inside a vessel that is highly dependent on the temperature and composition of the fluid, which changes greatly as reactions progress and generate heat. Our approach was to combine all of the governing equations behind the chemical reactions, flow behavior, and temperature dependence of the system into one unified model. We were then able to develop this model and make it robust enough to be applied in almost any reactor, enabling one to accurately predict how a reactor will perform even before it's built.
One of the benefits of our solution is the ability to optimize the reactor. This can be done in a few different ways. The first one is by adjusting the ratio of the starting materials. We can tailor the molar weight of the final product, and this allows us to get the desired product that we want. Another way is that increasing the temperature of the reactor means that the polymerization reaction happens faster, but it can also mean that some unwanted side reactions creating byproducts we don't want also happen faster. So finding an optimal temperature between the two means we can have the highest production rate possible without tainting our product.